It's 3 o'clock. Let's get started. We're finally in the second half of the class. So first 4 weeks are done. Now the last 4 weeks. So assignment 4 was due yesterday and grades are posted. Assignment 5 is out yesterday and is due Sunday. So the main idea behind assignment 5, as we've seen before, is that you'll download the Facebook data set that we've talked about before, and you'll just do some more analysis on it. And so some of the things are that Facebook has, if you want to model a Facebook network, you use undirected edges because if you're friends with somebody, they're also friends with you. So I want to ask, maybe if there's some dependence on the order here. So I want you to take a look at if you just make the edges directed in one direction, is the graph still strongly connected? And if you make it the other way connected, is it still strongly connected? I don't know. So I just want you to be able to figure that out. It should be pretty simple. Sometimes we want to know what communities are here. Where are the communities? So what I want you to figure out is how many components there are. So in the undirected graph, so obviously if the graph is connected, then there's one giant component because every single vertex can reach every other vertex. But if it's not connected, then you have like these two or maybe more communities that can't reach each other. So I want you to figure out, are there such communities? Like, are they disjoint in this way? So you're just basically figuring out what method in network X can help you figure out how many components there are. Pretty simple. Yeah. But the thing is, here, I want you to, instead of just looking at the entire graph, I want you to figure out, if I just exclude all the vertices that only have one edge connecting them, so like what are called the leaf vertices, then if I exclude those, then is the graph still connected? Basically, I'm just only choosing vertices with degree at least 2. And so you'll just figure out how many components there are. If there's one, then there's one. If there's more than one, then you have 2 communities that are disjoint from each other. And what I want you to do after that is you basically do the same process, but keep upping the degree until I get separation. So obviously you can choose a value high enough such that every vertex is disjoint from every other one, but I just want to figure out at what point do you get disjointness when you get a disconnected graph. And I have another question. So you could have a property that you get to some value of I for the degree where you do get 2 disjoint components, but maybe if you keep upping the value of I, one component's going to disappear and you get back to 1. So it may be possible that the number of components goes up and then goes back down, up and down. So I just want you to see, does it ever return to 1? Or does it always stay at 2 and then keep going up from there? Pretty simple. I'll get back to this in a second. We worked with matplotlib when we plotted the vertex degrees. So what I want you to do is use the betweenness and closeness centrality functions in network X to basically plot what the values of betweenness and closeness are. So it's just being able to use some functionality in network X and also being able to plot something in matplotlib. And we talked about that last week. And some other questions on that. And so for extra credit, what I want you to look at are making the breadth first and depth first search forests that we've talked about maybe last week, maybe the week before. Based on the last item, when you upped that value of degree until you got at least 2 components, what I want you to do is draw the forest. So the trees corresponding to each of those, right? So you'll be drawing a few trees there. So that should be pretty simple. And you can also make multiple figures if you want, because there are multiple trees that you'll make. And then another extra credit question that's pretty self-explanatory. So it's just doing a little research on what the name of a graph that has a certain property is. Okay? So any questions on this? So do Sunday. And yeah. You'll actually be making the graph yourself using NetworkX. So you'll basically code up in whatever file name you want. You'll basically write up what code you did to accomplish these, and also in this PDF you'll say the answers to the questions. So it's like, what value of I did you get, for example, for that question? Like, so basically you'll submit this PDF of your answers to the question as well as your code. Okay. Any questions on assignment 5? Okay. So just a few other things. The midterm is due tomorrow night at midnight. So a few people have been getting higher scores, so that's good. So keep up on that. And yeah, so it'll close tomorrow night. Any questions on the midterm itself? Okay, pretty straightforward. And if there wasn't already enough this week, you have your first project interim report, so which is due on Friday, I believe. So what you'll submit to me is what you've done so far in your project, what things have you researched, what things you have yet to do, if you have any questions for me, if there's something I can do to help you, any of that stuff. So if you have any questions on the project, please let me know as soon as possible so we can get everything straightened out. Okay? Any questions on midterms? So midterms due tomorrow night. The project proposal is due Friday, I guess at midnight, and the assignment 5 is due Sunday night. So every 2 days. Any questions on any of those? Okay. So for the material, we've been talking about dynamic programming, right? If I can open it. Yeah, there we go. So we've been talking about a lot of interesting problems, both related to graphs and not. Some things related to Indiana Jones, for example. Some of them related to biology, being able to figure out subsequences of things related to video processing, especially with longest common subsequence. A lot of different problems we've been talking about. So the main theme through all these problems has been store previous computation, and the computation that you have not already computed, try to make it as efficient as possible by looking at previous computation and then just reconstructing the solution based off that. So just as an example, what's an easy example? I'll just go back to Fibonacci. So Fibonacci, the naive implementation we had was that since the nth Fibonacci number is equal to the n-1th one plus the n-2th one, what we can do is we can just make a simple recursive algorithm, right? We have some base cases, so if we were either the first or the second number, then we return 1, because those are the values. Then otherwise, we just recursively call ourselves by calling the n-1th number and then the n-2th number. And the problem we saw with that is that we're doing computation over and over again, right? Like if we expand this recursion out, we see that we actually do 2 calls to n-2. And we only really need to do 1, right? We don't need to do that same computation twice. So what we figured out was we can just store previous computation in a dictionary or an array or whatever you like. And so what we did here is we first check if the lights went off again. All right, so if the particular value is already computed, basically it means in the dictionary, then we return the value corresponding there. Then otherwise, we haven't computed it yet, so we just do the computation. So if we have our base cases, do the same thing. Otherwise, then we do the recursive computation. But instead of directly returning here, we're going to store this result in first, then return it, right? So in future computations, I won't need to do these 2 recursive calls, right? So what we were able to see through simple analysis of the big O notation and also the runtime when we actually implemented this is that this is way faster. An exponential time algorithm, we found out, versus a linear time algorithm. So dynamic programming can get you a lot of power here by just simply by storing previous computation and not doing it over again. Any questions on what we've been talking about so far? All right, so let's talk about a few more problems and hopefully we'll finish up this today. So how many of you have played Crazy Eights? So it's basically a card game. So I'm not going to go too deep into the details of what Crazy Eights is, but there is an algorithm to figure out the best sequence of choosing cards in Crazy Eights. So the Crazy Eights game is basically each player is given 8 cards from a standard deck, say 52 cards, or maybe more. And each player in turn matches the rank or suit with the top card on a given pile. So you have these people sitting around this deck of cards that hasn't been given out to players yet. And so you go in turn, and then you look at your cards and see if you can match your card to the top card on the pile, either with the number, so if the top card, say, is 5, I want to put down another 5, or if say the suit is hearts, for example, I want to put down another heart, right? And so that's just the basic game. And of course, you may be wondering, okay, maybe I can move, but what if I can't move? Well, if I can't move, then I'm going to keep drawing cards from this pile until I can make a move, right? And so, and what the 8 has to do with this is when you play an 8, either by doing the same rank or via the same suit, but you play down an 8, you declare the suit for the next player. And so they must match this, and they're required to match the suit or play another 8. And so if we, of course, there are only a finite number of possibilities, so we can make this a constant time algorithm. So if we make this more general, so we're given n cards instead of, say, 52 cards. And each card has a suit and a rank. And so you're given a sequence of those cards. So maybe it's the order of the cards in the deck. And so what I want to do is you're given this sequence of cards in some order left to right, maybe. And I want to be able to find the longest subsequence. So it's kind of like the longest common subsequence problem we've seen before. Choosing specific indices of these two strings such that if I read off the characters, it's the same in both strings. And the problem we had there was we wanted the longest subsequence. So here, what I'm given is this sequence of cards, which has a suit and a rank on each one. And I want to be able to find a match. I want to find the longest subsequence I can so that I have a match when I go through the entire thing. So what I want is that each consecutive pair of cards has either the same suit, they have the same rank, or one has rank 8. Okay? So that's essentially the problem that I'm dealing with here. So I want the longest subsequence of this list of cards, and I want to be able to find that such sequence such that each one that I choose from this long list has the same suit consecutively, or the same rank, or one of them has rank 8. Because if I choose rank 8, then I can choose the suit for the next one anyway. All right, so what we want to do here is we want to define this function, choice of I, to be basically the length of the longest subsequence, starting with the ith card on. So it's kind of like the longest subsequence problem. Like for the array that we defined, index I corresponds to the longest subsequence up to index I. I could do it analogously here, but I'm going to do it from the ith card onward. Okay? And so I want to look at every single card after the ith card, and then be able to choose the best one from, be able to choose the best subsequence from there, the length of the longest subsequence in that from I onward. So it's essentially this. It's basically I choose card I, and it's basically the best choice of the next card in the sequence, right? So the next card in the sequence would have the best possible choice for its card onward. So I want to choose the best one from the ith card to the end, right? But we also want to make sure that the card J that card J matches with card I, because if it didn't match, then we would have a problem, right? Because I got to have this property that consecutive cards at the same rank, the same suit, or one of them is has rank 8. So we can do that in constant time, but I'm just telling you, you would have to account for this. So therefore, we have an algorithm to solve this. So how would I solve this? Well, let's see. Choice I is looking at all cards from itself all the way to the end. So what thing do I want to return? I want to look at the best choice of cards through the entire list, right? So that's essentially what choice 1 is, right? It's the best choice of cards starting with choice 1 onward, right? So I'm going to return choice 1. So I want to start building this bottom up. So what I'm going to do is I'm going to start at the end and then work my way towards the front of the list. So I'm going to start with choice n, then I'm going to go to choice n minus 1, see if I can work with those two cards. Then I go to n minus 2, look at those 3, n minus 3, look at those 4, all the way until I get to the very beginning of the list, right? And so so if I have n cards, if I'm looking at choice I, how many cards am I going to look at, possibly? Well, it's from I up to n, right? So n minus I, essentially. So if I want to do this for I equals n minus 1, I equals n minus 2, I equals n minus 3, all the way to 1, how many cards am I going to look at?
N factorial. Or I minus n factorial?
Way less than n factorial. So I may have order n for each value of I, right? And how many choices of I do I have? N minus 1, n minus 2, I have n choices. So n choices and n things to look at for every single choice. This is an n squared algorithm, right? It's pretty simple, right? So it's just saving previous computation because I'm assigning to choice I what the best, the longest subsequence is. I can actually store the actual subsequence if I want to, but I'm just keeping it easy. But the main point of this is that I'm saving the previous computation and then restoring it later. So what I'm looking at is when I save into I minus 1, if I save into I, then when I go to I minus 1, I'm going to look at every single one after I minus 1. And then once I store into I minus 1, look at I minus 2, then try it again. Okay? So any questions about this? So it's just a simple algorithm that it doesn't have to be applied to graphs or strings like that. It's essentially a fun game that people play. So that basically means that dynamic programming does not have to apply to things we normally study in computer science, right? This type of paradigm of storing previous computation can be applied anywhere. Any questions on Crazy 8s? Yeah.
I'm still kind of confused how there's n choices.
Yeah, so what I'm basically doing is I'm building this bottom up, right? So choice n, so for the nth card, I either include it or I don't. So n minus 1, I want to look at from n minus 1 to the end of the longest subsequence that I can include from there.
Oh, so for each one you're choosing whether
Yeah, right. Yeah.
Wouldn't they have to be next to each other or adjacent, I guess?
Well, what has to be adjacent?
The two cards, wouldn't they have, I don't know.
Yeah, so
Like the n card needs, and the n minus 1
Yeah, so the key here is that it's subsequence, right? So a subsequence, if you recall, is essentially you choose not necessarily consecutive places. So, and if I read off of the elements in there, I want to make sure that the properties are maintained. So the properties that, if I read off of these choices in this list, this subsequence, then each consecutive element has the same suit or the same rank. Okay, so the point here is that it's a subsequence, not a sublist. A sublist is different than this. Yeah. Mm-hmm. Any other questions on crazy gates? Okay. So now you're wondering, you've talked about graphs, you've talked about strings, you've talked about, although this is fun and people actually play card games like this, why don't you do something that's actually applicable to me, something that I actually care about, right? So this is what the next big problem that we're going to talk about is next. So, which are called context-free grammars. So has anyone heard of a context-free grammar? So I'm going to define it first, and then I'll tell you all about the applications of it. So a context-free grammar has 4 parts. So the 4 parts are V, which is the set of what are called variables. Sigma, which is that summation symbol, is just a set of terminals. I'll define all these in a second. R is a set of rules. So basically, you are applying rules that convert a variable to a set of either terminals or variables. And there's a special denoted variable called S, which is called the start variable. So what you're doing here is you start with S, then you keep applying rules over and over. And then, so here's an example CFG, context-free grammar. And so what we're given is a string W, which consists entirely of terminals. So maybe, so in this grammar, it's not really specified, but it's, the convention is that the capital letters mean the variables, and the lowercase letters mean the terminals. So if I look at, let's just see this. So the goal of CFGs is you're given a string which consists of these terminals, in this case A and B. And what I want to figure out is maybe like A, B, for example. I want to determine if this grammar, if you apply rules over and over and over, I can get that string, right? So let's just look at that one string, A, B. No, I don't want a kebab. So,
something from like the Bacchus and narrower?
It's essentially BNF, yeah.
BNF, okay.
Yeah. It's essentially that, but this is like a more abstract notion of that.
Okay.
I'll get into something that's kind of like that in a second. So we have these variables, and I'm basically, if I want to apply a rule, so the way that these are written is that S has a rule that can transform it into A, capital S. So either I can apply that rule, or, so this vertical bar means or, I can replace any S with BX, right? So it's basically, you start with capital S, which is the start variable, and I apply one of the rules on the right-hand side. And then since I get some variables left over, either the S or the X, I apply a rule again. And then I apply again, until either I get into an infinite loop in a sense, like I can't ever get into a string just full of terminals, or I get the string that I want, or I can't get it at all. Okay? So here I must start with S, right, because it's the start variable. So I have 2 choices of a rule to apply. So either the A capital S or B capital X. So which one should I apply here? I must apply the A one, right? Because if I apply the B one, then I can't ever get to the left of B to generate more A's. So I can't apply that rule. So I have to apply AS. So Now what rule do I apply? Well, since I generated the terminal A, I can't ever replace it with another rule again. So the next character I have to generate is another A, right? So I apply the S goes to AS rule again. So AAS is now what I get. Now I get S goes. I need to generate a B, right? Because that's the next character I have to make. So I have to apply either S goes to AS or S goes to BX. So of course now I have to apply the BX rule. So BX. Let's make this bigger. So now I'm at X, at X's rules, right? So I'm not at S anymore. So the next character I have to make is little a. So either I have to apply the AX rule or the BY rule. So obviously I have to apply the AX rule because I have to generate A. So AAB, AX. Now I have to generate B. So I can't apply the AX rule, so now I'm going to apply the BY rule. So AAB, ABY. And so now you're thinking, oh, we just generated that entire string, right? Yeah, we generated this entire string, and we have this variable at the end, so we don't have a string entirely full of terminals now. We still have this variable that I need to try to apply one of its rules. And since I don't have anything left in the string, I can't apply any of the rules. But there is a special character for context-free grammars called the empty string. So kind of like empty string in programming, it's an empty string here. So the symbol is called lambda. Sometimes it's called epsilon, but here it's called lambda. So lambda here means that replace the variable with an empty string, nothing, right? So obviously I can't apply the y to AY rule, right? Because I'd be generating another terminal that I don't have in the input string. So I can't do that. I can't apply the B to Z rule for the same thing. Can I apply this rule? Y to empty string? Yeah, because if I replace Y with empty string, I get the string that I want out. So therefore, I say that this grammar derives AABAB. Okay? So, yeah, I don't want a kebab. But you see the point, right? I start with the start variable, then I apply one of its rules, so basically replace it with something on the right-hand side of it, and then I do it over and over and over again, and hopefully I can get the string that I want out of it. Okay? Yeah.
So back at the beginning, where you have AX.
Mm-hmm.
So since you have A uppercase S,
Mm-hmm.
you have to go back to the S rule again.
Yeah. Yeah, so it could be possible that I have a rule that looks like A, S, B, 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 X, Y, Z, C or something. So I could have a mix of terminals and variables. And so since those terminals are fixed, I can't apply a rule to them. It doesn't matter which one I pick. Right, so I can either start working with the S variable, or I can start working with the X or with the Y. So although sometimes there definitions for some terms make you start with one variable over the other, but since they're fixed, there's no reasoning that I need to start with one or the other. Right, so it doesn't have to be in this form, one terminal, one variable, or some, yeah. So. Yeah, because this is actually easier than a context-free grammar anyway, but I won't talk about that. So the point here is that ABABA or kebab, all right? No, stop. What do I say about doing live demos? Never do them, yes, right. But the point is clear, right? So you're applying rules in the grammar, over and over and over until you either get into a string entirely full of terminals, which is the one that I want, or I don't. And it could be possible that I could have, say, AS or AX, right? So if the starting character is A, either I can go into the S recursively, or I can go into X recursively. So it may not be so simple as the one we have where you have a choice between them, right? So the point here is that what I want to figure out using dynamic programming eventually is, given a string and a grammar, I want to figure out if this grammar can generate that string. That's my goal here. Any questions on this? On the definition? Okay. So now I'm going to talk about applications of context-free grammars. So anyone take CSE294 before? Okay, so it's a really cool class. So it's actually very highly used in compiler design. And if you actually go to the Python docs, it's actually not quite a context-free grammar, but it's very close to one. If you look at here, it's essentially a context-free grammar. So, like if I have a variable called single, so what they sometimes use for terminals, the things I want to generate, are sometimes all in caps for compiler designers, and the variables are all lowercase. So here I have a variable called single input, and either it can generate a new line character, or I recursively go to the simple statement variable, or I can go to the compound statement variable, and after that with a new line character, right? So the new line here means terminal. It doesn't mean that I can apply a rule to it. So it's like the lowercase a, b, and c we've seen in our example. Cool. So they're used a lot there. And how they're used is when your program, say like if you're compiling in Java, for example, when it says that you have a missing curly bracket somewhere, or this statement is not quite syntactically right, a context-free grammar is verifying that for you. So on the back end, your program is just essentially a giant string that you feed to this context-free grammar. And if the context-free grammar says, yes, we can generate this string, therefore your program is syntactically correct. Okay? So that's a very large part and a big headache of designing compilers. Being able to design what programs you can generate using a context-free grammar on the back end. So these things are used heavily there. And they're used what are called modified context-free grammars, so there's a little bit of a difference there, but it's very subtle. But essentially it's a context-free grammar on the back end. You can use this for representing knowledge in natural languages. So in the same way, you can actually represent, like, say, how a syntactically correct English sentence is. So it's like subject, verb, something, maybe another clause or something like that. So you can represent that as a context-free grammar. They're used in what are called models of computation. So being able to reason about what kinds of things can computers do. Context-free grammars are above what are called the regular languages. So there's a level of what are called context-free languages, and then above that, there are called what are called the decidable languages. So it turns out that there are some, I guess, ways, there are some sets of problems that context-free grammars can solve. So like maybe there are some programming languages that context-free grammars cannot model at all, right? So it turns out that there is a distinction there, but they're used in this setting also. There are actually many types of grammars. So, and there are actually what are called normal forms, and we'll get into one in a second. But context-free grammars are the most common because they have a huge number of applications. All right. So any questions on applications? Okay. So main goal, as we've said, is we got this string W and we want to figure out if the grammar that we have can derive that string. So starting with the start variable, apply rules over and over and over until I get W, or I determine that I can't derive it at all. Okay, so that's my goal. And this is analogous to one of those applications. I want to figure out if the program that I'm given is syntactically correct or not. And if it's not syntactically correct, then the grammar that corresponds to this language can't generate that program at all. Okay? So that's essentially my goal here. So the problem is that if we want to analyze context-free grammars, it's pretty unbounded, right? So like the example we saw that we could, instead of just having one terminal with one variable, we could have anything on the right-hand side. Of course, we can only replace a variable with other stuff, so we can only have a variable on the left-hand side, but we could have anything we want on the right-hand side. So I can have A, capital X, B, 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 X, S, A, B. You get the point, right? So I can replace a variable with anything that is on the right-hand side. There's no structure to the right-hand side, which makes the problem, you can still do it, but it's a lot more difficult, right? So what we're going to do is we're going to restrict the problem, not really restrict it, but make the problem easier to think about. So what time is it? So I think a good time for a break is now, because the next thing will take a little bit of time. So let's take a 10-minute break. All right, we are back. So we've been talking about this thing called a context-free grammar. And what it is you're given this string W and a grammar G, or whatever it's called. And what I want to do is I want to figure out if the grammar can generate that string, starting with the start variable and then applying rules over and over until I possibly could get the string. Okay? And so it has several applications in compiler design, natural language processing, many applications. But the problem is that for context-free grammars, there's no restriction on what can appear on the right-hand side of a rule. It's quite complicated, right? So what we want to do is we want to structure the grammar in an easy-to-analyze way to make figuring out using this dynamic programming strategy that we'll talk about much easier. So what we're going to do is we're going to convert our grammar into what is called Chomsky normal form. Anyone know Noam Chomsky? So he's the father of what is called the Chomsky hierarchy, which is basically what those models of computation I talked about, what types of problems that they can solve. So he created this form called Chomsky normal form, which is essentially an easier to parse version of normal context-free grammar, different normal, but it's easier to parse this type of context-free grammar. And so what a Chomsky normal form is, I will go to an example. So what these are is basically, instead of having a really long or really short right-hand side, we're going to have either the right-hand side is two variables, right? So a variable can be replaced by exactly two variables or one terminal, right? So instead of having a mix of terminals and variables, either I have exactly two variables or one terminal. And I forgot to include something here, and the start variable can make the empty string. So it's not like the grammar before where we had either Y can make the empty string or Z can make the empty string. Only the start variable can make the empty string. And the reason for that is that anyone hear of ambiguity? So what does ambiguous mean? So it's not sure. Either I can do this thing or this thing. So ambiguity in a grammar means that for this string W, either I can choose this rule or I can choose this other rule, right? So it's not like the example where we had exactly one choice to make. Either I can go this direction or this direction. So if I wanted to make the empty string, obviously I'm not starting with y, but just bear with me. Either I can go y makes empty string or z makes empty string. There are two ways to make the empty string. So if I restrict it to being made by the start variable, then I only have exactly one way to make it. Okay? And so there's a theorem that we're going to actually look at now, which is basically we can convert any grammar into Chomsky normal form. So there aren't any that will be excluded by this. So therefore we are justified in converting our grammar into CNF and then working with that grammar. All right. So this is just a little taste of CSE355 and all the cool things that happen with it. So what I have here is I have a grammar. So this is the set of variables. So s, x, and y are variables, which are also everything that's capitalized. So it's easier to look at. A and b are the terminals. So my string that I want to match against is a set of a's and b's, or it's an empty string. R is the set of rules, so these are the rules. So S goes to AXBS, so that lambda means empty string. So it's not exactly the same as before, but it means empty string. So the empty string is here. I have some other rules that I can make also. And S is the start variable. So typically it's written at the top, but it doesn't have to be. So let's just look at an example. So let's just test the string. Let's just do the string we had before. Not that one. Stop. All right, so let's figure out what we can do. So we have to start with the start variable, right? Because it's the start variable. So S goes to, well, I have two, not really choices, but I have two, I have a choice to make here. So either I can make the AXBS rule, or I can make the epsilon rule. So the, not epsilon, lambda rule. So the empty string rule. So which one am I going to apply here? AXBS, because empty string is not a variable, so I can't replace it with anything else. So I have to do AXBS here. All right, so now I have a choice to make either the X part or the S part. So I'm just going to make a choice. I'm going to do the X part first. So this A, I can't modify it any further, so I have to write A. So what character does X have to make here? It has to make an A. So I have two choices. Either I can make a Y or A. So let's just make a choice because I have to generate I have to generate A no matter what. So maybe I could have here are the two possibilities. Either this B right here is the second B in this input string, or it's the first one, right? So so basically two choices. Either the B is the last one. So therefore, what does S have to be? It has to generate lambda. Good. Right? Or we have the B is the first one. So what does S have to generate then? It has to, of the input string, it has to generate AB, right? Because that's the order it has to go in. So S goes to AB. Oh, and back here, if this B was the last one, what does X have to make? So it has to make this middle part, right? Yeah. So X has to make. So what I'm writing here is not. It's not the actual rule. It's what it has to make eventually. So here, if this B is the first one, so what does X have to make here? It just has to make A, right? So what we're going to do is we're going to choose one of those, and then we're going to recursively try it. And then if we can't make that choice, try the next choice. Does that sound familiar? Backtracking. So there's a simple backtracking way of doing this. And if you look at this, each rule is going to generate either 0 or more characters for the input string. So essentially, this is an exponential time algorithm, right? So just doing simple backtracking and going back, right? So so now I want to be able to convert this grammar into CNF. So let's see. Let's format this nicely. So now what I want to do is I want to make sure that this grammar either has 2 variables on the right-hand side, or exactly 1 terminal, or has start variable goes to the empty string. So I should not say epsilon, I should say lambda. So does this grammar conform to what I want? So let's see. So we do have start variable goes to lambda, right? So we're good there. We have some rules where x, say, goes to A, y goes to C. That's good. We want 1 terminal on the right-hand side. That's allowed. But we have these other ones. So we want exactly 2 variables on the right-hand side. And here we have 1 variable on the right-hand side. Here we have a mix of terminal and variable. And here we have a whole bunch of mixings here. So clearly our grammar does not conform to what we want. So what we want to do is we want to convert it. All right. So the first step here is, well, we want to make sure that we can only generate that empty string exactly the very first step, right? We don't want to come back to it later, right? Because we only have exactly 1 chance to do it. So the first step is to make sure the start variable, or just make sure S is not on any right-hand side of a rule. And I'll post this, so don't worry about writing it down. So why would we want that? We want to make sure that we don't recursively call S. We want to make sure we either generate the empty string right away, or if we don't, then we just go into the recursion below. We don't recursively call ourselves. So the easiest way to do this is to make a new start variable called S0, and then we go to the old start variable, right? So we start with this new start variable and we go to the old one. So S0 goes to S, and then everything else remains the same, right? Because of course I'm not going to generate any more strings or any less strings than I did before, right? Because anything that S can generate, S0 can certainly generate also, right? So I'm not going to generate anything more or anything less. And we avoid the recursion problem, right? So although we have not solved the epsilon problem, don't worry about that, but we solved the recursion problem, right? We're not going to ever go back to S0. We're going to only go back to S. So here S0 is now the new start variable. Okay? Everyone good at what we're doing so far? So it could be quite confusing to even third-year undergrads here. So I just want to make sure we're all on the same page. Okay. Cool. So we want to make sure that S is not on the any right-hand sides of any rules. Cool. So now the second step is I want to solve that lambda thing, the empty string, not belonging to any variable other than the start variable, because I want to only generate it right at the beginning. So we see here that S, which is not the start variable, can generate this empty string. And we can recursively generate the empty string over and over, which is not good. So what we want to do is eliminate all of these lambda rules. So essentially what we want to do is look at all variables that can generate it. So what variables in this present grammar can make this empty string. Just s, right? So what we want to figure out is either s can, as it exists now, can either make a string or it might not make a string, right? So it either makes epsilon or it makes some other string, right? So what we want to do is we want to model both of those possibilities, right? So either s is just a variable by itself or it's just the empty string. So we want to model both of those. So what we are going to do is we're going to look at each place that s exists and then replace it with all possibilities for which it might not exist. Okay? So we're going to start at the beginning. So s, for the very first rule, s0 goes to s. Either s makes something or it doesn't. So therefore, I add a rule for generating when s does not exist, which is here. Okay? Pretty simple. And obviously, I'm going to eliminate this rule because I can't have s generating this. But here, this is the only other place where s appears on the right-hand side, right? So either s exists or it does not exist, right? So either I'm going to generate this as it is, or I'm going to generate it without it, right? So either it makes the empty string or it doesn't make the empty string. So I'm just modeling what it did before, but I'm forcing where the empty string appears in exactly one place. Okay? Pretty simple so far? Okay. And of course, if I had a rule that had, let's just say, ax, b, s, as, so now I have two possibilities where s could have been. So what I would do there is I would look at all possibilities of where s could be omitted. So either both s's are there, exactly one s is there, or neither s is there. So I'm going to look at every single possibility. So either it looks like this, or like this, so the second s is gone, or the first s is gone, or both of them are gone. Okay? So essentially what I'm doing is I'm looking at all possible subsets of this, but you see the point. I'm looking at all possibilities of where s could generate the empty string, and just looking at when those can happen. Okay? So now we're going to deal with the problem of really short right-hand sides. So what we want here is we want to have exactly two variables on the right-hand side, right? So either we have exactly one variable on the right-hand side or three or more. Those are the ones I want to deal with, right? So what we're going to do first is we're going to look at the ones that generate exactly one variable first. So let's just look at this for a second. So what we're going to do is we're going to eliminate what are called unit rules. So rules with exactly one variable on the right-hand side. So I'm just going to copy it here. So what's an example of a unit rule in this grammar? S0 goes to S, right? The rule itself. So what's another one?
Y.
Oh, yeah, Y goes to X, yeah. So that's another example. And I think those are the only ones, yeah. So what I want to do here is I want to eliminate those. So what's a really easy way to eliminate those? Just copy everything that belongs to S up to where it is on the right-hand side. So what I'm going to do here is I'm going to copy what S can make up to here, right? So I just eliminated that unit rule, right? And then we're just going to keep doing this over and over and over until I eliminate all unit rules. So is there a unit rule still here? Y goes to X, right? So now I'm going to copy everything from X and put it in the place of where X is, only for the unit rule. Not anywhere else. So I'm going to copy it down to here. Okay? So now we just eliminated all the short variable right-hand sides. So now the only thing we need to worry about are, so the the empty string one, where S0 goes to empty string, we got that, that's good. We don't have any variable goes to exactly one variable anymore, which is good. We have some examples of variable going to exactly one terminal, which is good, because we want those. But we still have this problem of mixing of variables and terminals, and some of them which are quite long, because I want exactly two variables or exactly one terminal, right? So I want to be able to deal with that in two steps. So what we're going to do now is we're going to deal with the mixing problem first. So what I'm going to do is I want to have the grammar right now to either have exactly one terminal on the right-hand side or a bunch of variables, right? And then I deal with the bunch of variables later. So there's going to be a choice. Either it's going to be all variables or exactly one terminal. So what I'm going to do now is make sure the right-hand side is either a terminal, a bunch of variables, but not both, right? What's a really easy way to fix this? Wouldn't it be nice if I can just say, like, replace this rule with capital AX, capital BS, and with capital A, capital B being new rules? So what would those rules be? Capital A goes to little a. Capital B goes to little b. So that's what we're going to do. Capital A goes to little a. Capital B goes to little b. And so now I just start replacing in my grammar. So here it's going to be capital A, capital B, capital A, capital B, capital A, capital B, capital A. Oh, should I fix this one? Why should I not fix it? Right, it's a single terminal. If I make this a variable, then I just made a unit rule, right? Where exactly one variable's on the right-hand side. So, and I don't want that. And it was already fine before, so I'm not going to modify it and just fix that. Cool. So now we've pretty much fixed everything. We have some examples of two variables on the right-hand side, or one terminal on the right-hand side, or S0 goes to the empty string. So the only thing we need to fix now are these long right-hand sides that have either 3 or more variables on the right-hand side. All right, so this is the last step, thank goodness. So what we're going to do here is we're going to, for the long variables, we're going to make new variables to make sure that we only generate one at a time. So what we're going to do is break up long right-hand sides. So let's just do an example. So like that example AXB. So S0 goes to AXB. So how can I break up this long right-hand side?
C goes to AX.
So you would say like C goes to AX, and then what would I do to the original one? Right, exactly. So I make these new variables such that the new one has exactly 2 variables on its right-hand side as well as the original one using that new variable. All right, so that's exactly what we're going to do. So I'm going to use that example. So C goes to AX, and then just replace AX with C here. And now I have these ones to deal with. So how many? So if I have 4 variables to deal with, how many new variables am I going to potentially put in? 2. Yeah. So there are actually 2 ways of doing this too. So the AX could be replaced with C, and then what's the simplest way I can deal with this 3 variable one now? D goes to BS, exactly. Awesome. And I want to make sure that the variables that I make haven't been already made, but that's a minor point. So the BS can be replaced by D, and now let's see. So the grammar has obviously variables on the left-hand side. Either we have two variables on the right-hand side, or one terminal, or start variable goes to empty string. Oh, so we just converted our grammar to Chomsky normal form. So we got this nice normal form which has a nice structure to it, which will be useful later. Any questions on how we were able to do this? Okay. So there are, other than the dynamic programming of this, there are easier, it's much easier to parse context-free languages in terms of the size of the input. So you actually could figure out the exact number of rules that will be applied to generate a particular string, for example. So Chomsky normal form is used all over the place with grammars because of the properties that it has. All right. Any questions on what we've gotten through so far? Okay. So how many of you have heard of a parse tree? So a parse tree is essentially just like a certificate of how you derive this string W in the grammar. So I have an example. So if you look up parse tree in Google search, so maybe that's too small. I'll just make it bigger. So a parse tree is essentially a tree, for example. So the root node is the start variable, and the children of the start variable are what it can generate. So it can, let's just say that we had say, we'll make a new one. We had S goes to AXBS, for example. And so if we look at the parse tree for this, the start variable S would be the top node of this tree. And a leaf, it would generate A, then a new internal node X, which will generate other things. So a leaf node A, an internal node X, a leaf node B, and another internal node S, right? So it's essentially, the parse tree is modeling what happens in the derivation of a string, okay? And a parse tree is unique to a given string in a grammar. So there isn't a parse tree for a grammar, for example. So it's just helpful to think about what a parse tree does in terms of when you try to derive a string. And that'll actually be really helpful in designing the dynamic programming algorithm here. So in the internal nodes of the tree, we want to figure out some properties of this. So we converted our grammar to Chomsky normal form. So we have either two variables on the right-hand side or one terminal, other than that other rule, but two variables or one terminal. So what are the internal nodes of the tree? Not the leaves, the internal nodes. What is their structure? They're the variables, right? Yeah, they are variables. Except for the second to last level. So the second to last level, the leaves are, of course, the terminals that we're generating for the string. So the second to last level, are, of course, are variables, but they're going to be doing all of the leaves of the string we want to generate. But all the other internal nodes, how many children do they have? Why do I say they have two children?
Because besides the other ones that are generating the terminals have two variables.
Exactly, yeah. They're going to be generating two variables each, except for that second to last one. They're going to be generating two variables each. Cool. So we actually know some properties of the structure of the tree, which will be very helpful in our algorithm. And the last level, of course, are the leaf nodes, which correspond to the the string of terminals we want to make. So it's a binary tree because every internal node has two or fewer children, right? And so we know it's a binary tree for that. And so the goal is we want to figure out if we can make such a parse tree such that if we read off the leaves, it gives us the original string we had. Okay? So that's essentially what we want to do. And so we can verify this easily. So what's an easy way to look at all the leaves of a tree? We've covered it in 205, I think. You can do a modified version of any one of those order traversals, right? So either in order, post, pre. You can do a modified version of it that because the way it's structured is a little different. But you can go over all of the leaves in the tree and then just read out the contents of them, right? So it's easy to verify whether a parse tree actually gets the string you want, but the problem is, how do we make such a parse tree? Because, of course, there could be exponentially many of them, right? Because I have 2 choices at the beginning, then 2 more choices for each of those, all the way down. So I could have exponentially many here. So the problem is, how do we figure out whether the start variable could make the string that we want? And so what we're going to do is, we're going to do a bottom-up parsing approach. So our goal, just to reiterate, we want to make sure that S, or verify whether or not S could generate this string W that we have. So let the ith character of W be W of I, just as we've seen before. And we want to see if the grammar can generate the string W1 through Wn, so concatenated together. But it'll be helpful to write it in this way, from the start variable. So here's an idea. What we want to do is figure out what variables can make the exact first character, only the first character. What things can make the second character? What things can make the third character? ... What things can make the last character, right? So that's a start. So we know what variables can make each of the characters, but we want to figure out what variables, so essentially we figured out what can possibly exist on the second to last layer, the thing that can generate all the leaves. We know what could exist there, right? We just don't know what could happen above there yet. Any questions on what we've gotten to so far? Okay. Because it might be difficult to keep track of what variables would work, because there could be many possibilities for this. So what we're going to do is note that every single internal node has exactly 2 children. Why did we want to do it in Chomsky normal form? Because we have a bound on how many children a node can have. Whereas for the regular context-free grammar, it could be that it has a lot of children, and so we would have to make many choices. But having exactly 2 children, we can figure out from these 2 children what could be at the node right above them, right at their parent together. So that's exactly what we're going to do here. So let's consider a substring wi through wj. It could be the entire thing. It might be only one character. Let's just consider a substring wi up to wj. And so let's think about it. So if we figure out, say, variable a could make some split of the string, so maybe the first half of the string, variable a can make that part, and variable b can make the second part, right? Let's just say that was the case. And let's say we had a rule, c goes to ab. So what can I infer now? So a can make the first part, b can make the second part. And so c can make ab, so c can make this entire thing. That's essentially what the entire algorithm is. Okay? So maybe we can consider the first split could be a makes the very first character and b makes the rest of it up to wj, or maybe a makes a lot of it and b makes little. We have many possible choices to choose here. So how many splits are possible for a string from wi up to wj? Oh, what's that? It's
From W or J minus I.
j minus I. It's exactly that. Yep. Because we want non-empty here, but it's a minor point. There are j minus I splits here because what can happen? From wi, I can make the split at between wi and the rest of the string, or I can make it wi plus 1, split rest of the string, all the way through. So if you count, that's just j minus I possible placings of this split, right? So what we can do is, for each of these possibilities, we check if there's a variable that can make the first part and a variable that makes the second part, and then we figure out if a variable can make the first one and the second one. Okay? That's essentially what we're doing. And then, once we bottom up parse this entire thing, we ask if the start variable can make the entire string. Easy. So here's the algorithm. So I can't pronounce the authors are on the I think 2 slides from now, but it's a famous algorithm called CYK for the original authors. I think, I can't pronounce the names. So what we're given is we're given a string W. We want to figure out if G, this grammar, can make it. So they're also called non-terminals, but these are also called variables. So let's just say R1 is maybe like the start variable. We have little r variables that we can work with here. Okay? And so let n be the length of W. And so P is going to be a gigantic matrix. So what it is my notation's a little bit confusing, but essentially these first two are going to be about where the split starts and how long the split is. And what R is going to be for each of those n squared things, what variables could be generated for that split. Okay? So we have those two parts. We want to start with doing the bottom-up parsing, that second to last layer, starting with figuring out for each character what variables could generate each of those characters. So we're just going to iterate through the string, the first character up to all the way through the end. And so they're called unit productions, but we call them rules. So we're just going to look at every single possible rule that could, starting with a variable, say rj, that can make each of the characters. So like when on the first iteration, I equals 1, we look at every single variable that could generate W1, right? And so we want to figure, so if that's possible, then we want to store that we could do that. And then we go to the second character, look through all the rules again. Third character, look through all the rules. Fourth character, all the way to the very end. Nth character, what variables could generate that one character. So what I'm going to do is I'm going to set P of 1, I, j is equal to true. So what is the notation here? So the notation means this last entry means the particular one of the variables. So here it means the jth variable. So whatever rj means. I here means where the substring that I'm looking at starts. And what the first one means is how long after that start I'm looking. So here it means starting with wi, I only look at one character, right? And after that we're going to look at longer and longer sequences. And then, so basically now we're just setting what we can generate in one step to be true. And so now we're going to do that bottom-up parsing. Questions so far on that? So now what we want to do is we want to look at longer and longer splits, right? Longer and longer of these split sections where we look at the split. So at the very end, we're going to look at the very last one. So I equals n means the entire string, but starting with every possible substring of length 2. So here, don't worry about the upper bound, but j means looking at all of the where the split can start. So I means where in the string we're starting to look at, and j means how. No, sorry. I is the length of the split, of the split section. So like wi up to wj, and j means how long that split is, and k is where to split. So I is the start, is the length of the section. J is where we're going to start in the string, and k is where we're going to split it up. And so what we're going to do is we're going to look through every single rule that has two variables on the right-hand side, and see if B can make the first part of the split, if C can make the second part of the split. If those are true, then A can make the entire thing, that entire both sides of it. So here, what the notation means is that if B can make from the start of the split the first k characters, so basically where the split is, and C can make, starting from the second half of where the split is up until the very end of the entire split section, then A can make the entire thing, right? So A can make from the start of the split section the length of the entire split section. So essentially we're just doing a bottom-up parsing of the entire thing. And what we want to do now is we want to make sure that we can generate from the very first character the length of the entire string. So starting from the first character of length n. And so if we can return true here, then we return that the grammar can make the start. Sorry, the grammar could make the string that we're given. Okay. I know this is a little confusing, but especially on the bounds, but does the conceptual part make sense? Yeah. So essentially, we're just looking at longer and longer splits and looking at every single possibility that can happen. So it's kind of like smart brute force, right? We're looking at every single possible split that it could be, but we're making sure that we store the previous computation so that we don't recompute. All right. So here, of course, I can feed long strings to this grammar, right? It doesn't, they don't have to be short strings compared to the grammar. So what we usually consider is that the grammar is fixed, right? I can feed long strings into it, but the number of rules stays the same, right? So let's look at the algorithm again. So obviously the outer loop has order n iterations. The second loop has approximately order n operations also. K equals I to 1. Well, let's look at that. So I can go from 2 to n. So essentially that could be order n operations, right? But look at here. So we're looking at all rules of the grammar. And I just said that the grammar size is constant, right? So what is the number of iterations from these four for loops then? Well, we have order n times order n times order n times, well, how big is the grammar compared to the string? It's constant. The grammar is fixed size compared to the input string. So essentially, it's constant size, right? Because I can feed it arbitrarily long strings. The grammar stays the same size, right? So here, this for all of iterating over all the rules, that's constant time. It may take a long time, but in terms of the size of the input, W, it's constant time because the grammar we consider fixed. Sometimes we actually do factor the grammar size into account, but here we usually consider the grammar to be constant size. So essentially, we have order n cubed iterations here. So let's look. Two lookups into a table and then storing into a table, that takes constant time. So order n cubed times a constant amount of stuff, that's an order n cubed algorithm. The constant may be huge behind the O notation, but it's order n cubed in general. Okay, so we have 3 nested for loops iterating between 1 and n. And so we have one for loop over all the rules, which is of constant size. Looking up and storing into tables takes a constant amount of time, we assume. And so we have a n cubed time algorithm. Yeah.
Compiling code doesn't take what would be n cubed, right? Like compiling 100 lines of code is much faster than n cubed time in this. Is there a faster algorithm?
So as I said before, this is just a conceptual way of doing it. This is not how they actually implement it because, as I said before, that most programming languages don't use context-free grammars. They use something that's a little bit more powerful in terms of what they can compute. But you're right, n cubed is slow, right? Because this is just doing all the possibilities all at once. And I think there are faster algorithms than this. But I'm just reinforcing that this is a dynamic programming approach to this. And so the authors are Kok, Younger, and Kasami. And those were 3 independently published papers in the late 60s. And so basically it's usually called the CYK algorithm for their names. Yeah. So are there any questions on CYK or context-free grammars at all? How are we doing on time? Let's just do the very last one and then we can finish up. So text justification. So what this is I want to, let's just say I'm coding up Microsoft Word and I want to make sure that no lines go either very far over the width of the page, or the number of characters that is short from the width of the page is minimal as much as possible. Okay, so if you've played around with justification, it's essentially uniform on both sides. And so, of course, if you do it badly, then you have some lines where there's a huge space between words, right? And I want to avoid that as much as possible. So text justification is about trying to minimize the amount of space after a word. And so essentially what it is just we got this a bunch of words, and what I want to figure out is where do I make an enter press? Where do I start the next line? Like what word starts the next line? And so that's what text justification is all about. And so maybe we can fit the entire document on the line, right? That may be possible, but most of the time we can't, right? We got to make some enter or some choice. It can't just run forever. And so we got to figure out a way to split it correctly. So what we do is basically what is called a greedy approach. So anyone know what greedy approach is? Just do, at every point, do the best thing you can do in one step. And then do the next thing, best thing in the next step, best thing in the next step until you're done. So essentially this is a greedy approach. What you can do is you just fit as much as you can onto a line, and then you enter and start on the next line. Why is this a problem? Because it might be possible later that you have a really bad line, right? It may have been better to include another word from an earlier line onto the next line, and like incur some cost up here, but to make a large savings down here. So what I want to do is not a greedy approach. What I want to do is I want to do a smarter approach. So anyone have used LaTeX? Yeah, so it's the thing that I use to code up all of the assignment documents, which makes all the text look nice and uniform, all that stuff. Yeah, and sometimes if you've seen, it does the breaks in words. So instead of including the entire word or omitting the entire word, it does like half with like a dash to the next line. So sometimes it does that. So we could have very bad lines, right? We could have these lines that are really bad from doing something we shouldn't have done before. So we only talk about justified text, so left flush, right flush. So it's uniform on both sides. So we want to figure out what is the badness of placing a word on the line? So if it's like getting really close to the end of a line, or if it goes over a line, then we want the badness to be really high, right? And if there's a lot of room still left, then we put the badness to be low, right? That's intuitively what we want. So, for example, if we want, if the word exceeds the width of a page, then like the entire word just by itself exceeds the width of the page, then it's really, really, really bad, right? So we want to say, maybe like make it infinite or like some high power, something like that. So we want to find a split for each of the words such that there's a minimum badness score. So we're doing a minimum approach here for dynamic programming. So what we're going to do is we're going to define this function, badness of ij, to be the badness score from index word of index I, word to index j. And so, well, what we usually define this to be, you can define your own function, is that we set it to be infinite, so really huge if the word length exceeds the width of the page, because we can't even place those there. But otherwise, we define it to be something like page width minus sum of word lengths to some high power, like cubed, for example. So if the word lengths are really close to the width of a page, then it's close to 0, so it's like it fits nicely. But otherwise, it could be a very large number. Okay. So this is similar to how LaTeX actually does this. So the algorithm is we're given a set of words, and let n be the number of words. So what D is going to hold is all these badness values. So they're all zeros. Actually, that should be, yeah, it should be all 0, yes. So instead of doing this ij business, I'm just going to make this simpler by saying the D of I means the badness score from I to the end, right? So D of 1 is the badness score from the beginning to the end. So D of n, of course, is 0 because, unless you can't fit it, but I assume you can fit all words. So if I set it to 0 at the beginning, and then I'm just going to do a bottom-up approach. So from the n-1 word, I figure out what is the badness score of D of n-1. So if I included the rest of the string, what is the badness score of that? So it's essentially it's the minimum possible index that for which I can include it on a page, on a line. So I want to find from DI what the badness score is from DI to DJ, and I want to find the best DJ that I can for my party, I guess. I want to find the best D of J that I want, and so I'm just going to find what the badness score is from I to J, plus whatever badness score was at J, which includes from J to the end. And so I want to find the minimum one of those and store it back in DI. Okay? And then I'm going to iterate J over the entire thing. So that's essentially what we've been talking about. And actually this should say D of 1, but I want to return the badness score of the very first word, which is the very first element in the list. So any questions on that? All right, so let's just look at the runtime. So we have this for loop that goes order n iterations. And here, I want to find from I the best choice of j all the way to the end. So it's essentially like the algorithm we saw with crazy 8s, right? We just essentially start with the last element or the first element, and then we go back, and then from each one, we look through what we've seen so far, over and over and over. So essentially, what the inner part of the loop is doing is it's doing a linear search over the list. So we have order n iterations up here, and the one up here takes order n time, right? Because it's just doing a linear search. So therefore, we have an n squared time algorithm. Yeah, it's pretty simple. So like some of the other algorithms, like edit distance, where we made this matrix of size n times m, we had to store the entire n times m array. But here it's nice because instead of storing like maybe someone naively was doing it, from index I to index j, the badness. What we did here was we just looked at from each index all the way to the end, right? And so therefore we only need linear space to store this because it's just a number for each of the indices of the input. So just wrapping all of this up, the takeaways I want you to get from this is that we usually define the problem in terms of a recurrence. So we've seen this numerous times. We want to store previous computation whenever we can. We want to look up previously computed values so that we can make the computations for newly uncomputed values as easy as possible. That's just been the major thing we've seen. And we want to make sure that we don't look up too many times, right? Because if we look up many times, then that can increase the runtime of our algorithm. So like with the text justification one, we only had this lookup of size n. And if we had a lookup of size n squared, then we may need to look up a lot more things. But if we want to look up as few times as possible. So make it as efficient as we can. So any questions about dynamic programming? Cool. I'll see you tomorrow.